probably experienced this. It's harder to get that box moving, but once it's moving, it takes less force. Your kinetic friction is basically constant. It's over here in this region, and you'll notice that its value is slightly lower than that peak static friction value. Yeah?
Would you be able to write those equations on the board? The brown on the black, it's hard to read.
Actually, I'll just get rid of the color.
That works too.
So does the mu unit stand for friction?
Let me talk about that for a second. Okay, so that symbol is called the coefficient of friction. We've got the coefficient of static friction and the coefficient of kinetic friction. So in Greek, this is called mu. When you're writing your lab reports, please don't be lazy. Just actually go through and find the symbol for things, because I have to do that when I make your presentation. So show me the courtesy and do the same, and don't put in U, because it's not U, it's mu. Okay, so coefficient of static friction, coefficient of kinetic friction. So what I was saying on that graph, that the peak static friction is always higher than the kinetic friction. What the result of that, or because of that, is the mu sub s is always greater than mu sub k. So the coefficient of static friction is always higher than the coefficient of kinetic friction. And you can see the relationship in those variables. It's a linear relationship, so if your coefficient goes up, your friction goes up. Ready for a corny physics joke?
Yeah.
This comes courtesy of my corny high school physics teacher. And we had good lab floors that were made out of tile. And one morning, he spilled his coffee right in the entrance to the room. So he put up a little sign to warn people, and his sign said, "Danger, cat in the basement." Get it?
I didn't hear anything about except for cat in the basement.
Yes, cat in the basement. Because there's a low mu. Corny physics jokes. Yes. I have to share all my corny physics jokes. It's my right as a physics teacher. Oh, the other thing here. So, for the coefficients, there is no units. They're unitless because you've got a force equaling something times a force, the normal force. So, coefficient better not have units, otherwise you mess up that relationship. Yeah, so the normal force, we just saw in this picture, if an object is flat on the ground, the normal force is pushing up on it, gravity is pushing down on it, so the normal force equals the weight of the object. So this makes total sense. Your friction increases when your weight increases, right? Because you can substitute, instead of normal force, you can substitute in mass times gravity, which we just learned is called weight. Right? So you can substitute that in and say your friction force is directly related to your weight. The heavier the object, the more friction force there's going to be. It makes total sense. Heavier the object, harder it is to push. Rachel?
So I was thinking that N was newtons, but it's normal force?
Yes.
How would we be able to tell if it's normal force or newtons?
When we write equations, we'll never have units in the equation.
Oh, okay, I get it.
Yeah. Very, very good question. Thank you. Oh, friction always opposes the motion. So the direction of the friction force, if you're trying to pull this box to the right, that's your applied force. The friction force will always be opposite to the motion. So if the box is actually moving, this would be kinetic friction. If the box is not moving, then it would be static friction.
So the coefficient for static friction is larger than the coefficient for kinetic friction. That's because
It's a tighter bond when they can sit for a second, and then these little crevices sort of settle into each other. But once you're moving, they don't have a chance to settle. Yeah. And how you figure out the coefficient, because we're engineers, right? We figure this out by doing experimentation, basically. You can't buy a table and look up a spec and see the coefficient of friction for that table, because it's also dependent on what you're sliding on the table. So the coefficient for an ice cube sliding on that table would be much, much different than the coefficient for this rubberized stapler. So how we figure out the coefficient is we have force gauges and we pull things across the table and see how much force it took. And that's a super fun experiment. But you'll have the joy of doing it. We're not going to talk this year about fluid resistance or air drag, but those are other examples of friction. Yeah, Robert?
What if the mass of an object is so great that it overrides the force of the friction? Like, say, you have Velcro. Both sides have Velcro. If you push like a baseball across the room, that's a lot of friction. But if you push like, I don't know, something really heavy like a table, it would just override the Velcro and there'd be less friction.
Oh, you're saying once it's already
That's true. Yeah. Once it's moving, the friction's less. It's just mushing Velcro.
Right.
So that has to do with the material
Uh-huh.
between the two.
Yeah, these are material dependent quantities. That's what we say. These are material dependent quantities, and you'll encounter a lot of that in your engineering courses. Things that are just properties of the material.
So how do you find the coefficient depending on how heavy it is?
You would have to do it experimentally. So you would have to just have a way to measure force and just pull things across that surface over and over and over again. Change the mass over and over and over again.
It's like tabulous.
Yeah.
The coefficient doesn't change with mass, does it?
No, but you collect you collect a plot, right? And then you plot it, and then you get the slope, and then you get the coefficient. Yeah. We'll do that in a lab, so you'll see exactly how to calculate the coefficient. And it's not that exciting, but it's worth doing. So anyway, I don't know. I always like come up with these little stupid things in my head to remember equations. So mine is friction is fun.
What does that mean?
Well, it looks like fun, right? The equation
Oh.
looks like fun, doesn't it? Doesn't it look like fun, guys?
That left a long time ago, just the way a few kids, what's fun?
Okay. Where are we for time? I feel like this is why this would be so much more effective class time if we could just problem solve. Okay, spring force, I don't know why your book doesn't put it in the force section, but it doesn't. So I'm introducing it, but you're gonna have no spring force problems this week. I just feel like it's a force, so I should introduce it. Spring force is governed by Hooke's law. Hooke's law says that the force of a spring is equal to minus K times X. K sub SP is the spring force constant. Again, that's a property of the material. So that is something you can look up in the table. Assuming that the spring hasn't been used too much, the spring force constant should be what it's listed on a spec sheet for a spring. The spring force constant is related to, well, anyway, it has units because the other term x is how far you stretched it. So the further you stretch a spring, the harder it's going to be to stretch the spring. So the spring force increases as that x value increases linearly, right? That's a linear pattern right there. F equals minus x. Yeah.
Sorry, when the spring is fully stretched, can you consider it like a rope where tension is equal uniformly?
Stop stretching.
If it was not changing its stretch,
Yeah.
then all points along the spring would have that same tension. Yeah. But yeah, as you change the stretch, the spring force resisting that is going to increase. And so spring force is a lot like friction. It always opposes motion. And they've incorporated a negative sign in the equation just to remind you of that. The negative is not a hard and fast thing. This is so hard to convey. You have to take that negative with a grain of salt, okay? Let's say you draw your picture. Here's your mass and a spring, and it's just hanging there. So gravity is pulling down on that mass, and spring force is pulling up on that mass, and it's in static equilibrium. If I were to do the sum of forces here in the y direction, my spring force is pointing upward. It is traditional that upward is positive. So my spring force is positive. My vector for mg is down, therefore it's minus mg. So when you put the signs on your forces, it's only because of how you drew your picture. So when you plug in your numbers in here, you cannot add minus k spring. You can't, because then you basically just said, well, that force is now down. So that minus sign is only there to remind you that it opposes motion, but you always have to qualitatively evaluate your situation and say, is it appropriate or not appropriate to add the minus sign? In this case, it would not be appropriate to add the minus sign because we need that spring force to be positive in order to cancel with the friction force. And then you get a 0 because it's in static equilibrium. So then we set this up, and now you have this spring force equals mg, and you can calculate stuff. So if the k, the x in this case would be how far it stretched from its unstretched position without the mass. So this would be your x value. If you can measure that, right, that's an experimental thing to easily measure, but you can use this relationship to calculate your spring constant. So just like with your coefficient of friction, you can experimentally calculate your spring constant just by hanging a mass on your spring. But if you'd accidentally put your minus sign in here, then your spring constant's going to be negative. But it's not a negative number. Okay, so I hope you've gotten the gist of what I'm saying. That negative is just a suggestion. Okay. All right, free body diagrams. I've already been drawing free body diagrams a bit. Here's one. Here's one. Here's one. A free body diagram is a simplified picture where you show just one object. And then you draw all the forces acting on the object. Only the forces acting on the object, like Jake reminded us, not the forces that the object is exerting. So just the forces acting on the object. Okay. You can also note things like, in this case, this object is moving to the right. So I'm going to maybe show the direction of the speed vector, but I'm not going to put that vector touching my object because I don't want to mix it up with one of my forces. So when I'm trying to build up my sum of forces equations, I'm only looking at the vectors that actually touch my object. This is useful information, but it's not a force, so I don't want to include it in my sum of forces equation. Keep your picture simple. You can show the surfaces or the objects, other objects that are part of the system, but you don't need to make these very elaborate drawings. And then what we have coming up next is just a whole lot of examples. Okay, and now is your guys' choice. We can do a whole lot of examples and break for lunch. We can take a 5-minute break and do some of the examples and break for lunch. We've got half an hour until it's noon, but I've been yammering away for an hour. So do you guys want a break right now, or do you want to just keep going through?
I think a break.
Okay, fair enough.
What do you want?
Me?
Want a break?
I could use a stop
Because I'd
talking.
rather have a fresh teacher than burn out or something.